Hello, so we start.
Yes, sir.
Okay, so my name is Bhane Mitra, and I am currently doing my PhD at Indian Institute of Science. So I'll be the TA of this course along with Orko, and the way it will go is normally we'll study all the video lectures and all. I am not going to pick up any topic. If you have any questions in the whole topic, or if you have any questions in the assignments, you will have to ask me. Okay, and I'll try to solve these problems and make sure that you guys are in page with me with the answers. Okay, so have you done the first assignment or the second assignment? Are those things complete?
So I've done the first week assignment. The second week is yet to be done.
Okay, so do you have any questions in the first week assignment? Or see, the way it will go is, for example, in this session, whatever subject you have studied, let's say discrete time signal processing, if you have any question in the theory or in the assignments, you will have to ask me here. Okay, so that's how the whole thing goes. So just admit that's the whole thing will go. So do you have any problem in the existing topics that you have studied? Any question? Though we know that discrete time signal processing is a very mathematical course, but we have to understand that the mathematics comes from intuition. Okay, so first the idea comes and then we represent the idea, because we cannot manifest the idea in some physical form and show it to the others. So we manifest the idea in form of mathematics and then we tell to the others. So first we have to understand that first comes the intuition, the idea, and then comes the mathematics. So are we clear with the intuition first for discrete time signal processing? Like
Yes, sir.
why we at all need to go to discrete time signal processing instead of analog signal processing? What is the problem? And are we losing anything when we are doing discrete time signal processing? Any answers? Any answer would be fine.
Yes, sir. When the sampling interval is very much high, retrieving the signal will be difficult because each and length between each and every when the TS is low, can be discrete time signal can be uh, transferred with less error.
Yes, Vishwanathan, right?
Yes, sir.
Yeah. See, but first, why can't we go for analog signal processing? What is the problem with discrete signal? What is the advantage we are getting with discrete time signal processing? Why can't we go with analog signal processing? See, are there any sensors? See, the signal processing is done on the sensor on the data of the sensors, right? So are there any sensors which are digital in nature? All the sensors are analog in nature. Then why we are going for digital signal processing or discrete time signal processing? Why can't we go for analog signal processing? Any answer? Yeah. Yes, Vijay, tell me. Yes. Please make it interactive, because I am also a student like you. So, yeah, tell me, Vijay. Vijay, I think you are on mute. You can unmute yourself and speak. Okay, no one? Yes, so Vijay left the meeting. Okay, so we do discrete time signal processing because finally there is a way to convert them into. Vijay, you have joined. You want to say something?
Sir, there was this interruption from my side.
Okay, okay. Yeah, do you have any answer for that, or do you want to say something?
So the implementation of the circuit happens to be in the real time. Okay, if we want to process any signals and we want to design any controller that has to be design the controller like in the FPGA on the DSP ports. In that case, all the signals has to be converted into discrete form, and uh, after that, the final conversion conversion of the signal has to be done into analog so that we can execute the signal in the real time, real life operation.
Yeah, absolutely. You are correct. But my question is, why to why to do the processing in digital? Why can't we do the processing in analog? Why you have to see the whole point of discrete time and all came because we want to convert the signal to finally a digital form for implementation. Why not to analog? We can directly do it in the analog.
Reduce consumption of power.
Analog will have actually less consumption of power compared to digital. In digital, you have very high consumption of power because there is continuous switching. We have this dynamic power dissipation in digital, right? Which is continuous.
Less footprint.
Hmm?
Less footprint.
Uh, Footprint is also less in analog, in fact, because a MOSFET, see, to implement an operational amplifier, you need only two MOSFETs, right? But or for example, a differential amplifier, you need only two MOSFETs. But to store a single bit, you need six MOSFETs in SRAM, or you need at least four MOSFETs to develop a flip flop. Okay, so good try, by the way, really good try. I could understand the perspective of what you guys have. Okay, so the reason we want to go for digital is because people are very comfortable implementing in digital. It is very easy to learn digital. Okay, and it is very easy to store the data. You cannot store the data of analog in various forms. Okay, because a capacitor will store a cumulative charge. A capacitor will never store a time dependent waveform. Okay, I mean waveform in the time manner, waveform with different time instants. A capacitor will never store that. Okay, a capacitor will store a cumulative charge. But in memory, if you convert that to digital, you can label the data in a timely fashion, and you can store the data with some timestamp. Okay, so that way you have this series of data which you can rather plot, which you can later analyze, and most importantly, it is very easy to learn C and digital language rather than understand, or rather than implementing or learning analog signal. Okay, or analog circuit. So that is the reason we want to go for digital. It is for us, it is for the ease of implementation of the engineers that digital has come. Okay, and most importantly, it is immune to noise. Okay, to some extent, not fully, to some extent. Okay, noise can alter the analog signal in a very drastic way. Okay, it can change the nature of the analog signal, but if you have a digital signal which is corrupted by noise, there are many ways in which you can recover the original digital signal, which you cannot do in analog. It becomes very, very difficult. Okay, and that is the reason we go for digital implementation. Now, to convert an analog signal to a digital implementation, there is a series of steps, which is the ADC. And once you have got the digital signal, the same kind of processing that you want to do for the analog signal, you want to do it for the digital signal as well. So for that, we need a course which is digital signal processing, and in this case, it is discrete time signal processing. Okay.
So how can we delay that? How can we deal with the delay that occurs in the digital signal?
Digital signal, very good.
Like if we use the A to T converter, which takes
Yes, yes, yes. You cannot deal with the
around
delay.
5-6 delay
Yes,
cycle after.
you cannot deal with the delay. You cannot deal with the delay. But see, most of the time, I was working in HL, so most of the time, we do not want instantaneous response. Even the response which is after 10 milliseconds is fine to human beings. Okay, we never want, for example, let's say that a helicopter is traveling. A helicopter is a basically inherently unstable system. Okay, so when a gust of wind comes, the helicopter, because of its weight and because of the speed, will take some time to go from stability to instability. Let's say the value is 15 millisecond. So as long as you are able to correct the course and you are able to make the helicopter stable within those 15 milliseconds, it is fine. We do not want instantaneous response. Similarly, for digital case, we do not want, neither we want instantaneous response, neither we want perfect accuracy. For example, if you are giving me 5 volts, even if I get 4.998, it is still fine. Or for example, if you are giving me 4.8 volts, if I interpret that as 5 volts, it is still fine to me. So that is the way engineering has evolved, that we are okay with the inaccuracies that digital signal is giving, because see, most of the time the value of g, the value of the acceleration due to gravity in the earth, it will continuously vary. It varies from 8 meter per second square to 11 meter per second square. But do we take all the time this variation in our calculation? No, we either take 9.8, we either take 10, and most of the time we take 10 because most of the calculations becomes very easy with 10. So this kind of small approximations and small errors does not affect the system performance in a great way, and that is the reason it is absolutely fine to have some kind of delay or some kind of inaccuracies in the digital system. We are okay with that, right? Who asked this question? Vishwanathan? Was it okay? Hello, are you guys able to hear me?
Yes, sir.
Yeah. So for example, if you have a delay of, let's say, 2 millisecond, let's say, which is given by, let's say, a flip-flop, you cannot alter that delay. You cannot go back in the past and change 2 millisecond, but that's okay. For example, let's say you have two signals, which is one which is having a delay of 1 millisecond, another one is which is having a delay of 2 millisecond. The least you can do is you can delay the fastest signal, which is the delay of 1 millisecond, by another 1 millisecond and bring both of them in time sync. That's the best you can do. You cannot bring this 2 millisecond, which is delayed by 2 millisecond, back to 1 millisecond. You cannot do that, because that is given by the ADC specification, that is given by the speed of the board, because the board will also have capacitance, the tracks. So all these things matter. But as long as it is within the tolerable limits, it is fine, because we always define a system performance in terms of error. So error is plus minus 5%, plus minus 2%. So all this error accounts for all these inaccuracies. That is manifested in some form by a digital system. Right?
So does delay reduce the bandwidth of a system?
Yes, delay reduces the bandwidth of the system, of course. But for example, uh, it is a very wide question. So if there is a continuous delay, okay, let's say, for example, let's say that 1, 2, 3, 4 data are coming. Okay, now 4 data, they are supposed to arrive at 1 millisecond. Now because of some delay, they are all arriving at 2 millisecond. Okay, so definitely there is a performance problem. Okay, there is a reduction in bandwidth, but this reduction is bandwidth if it is okay within the error limit of the system. If it is not okay, suppose, let's say you press a button. Okay, now the time to, in your mobile phone, let's say you press the back button. The moment you press the back button until the last page comes up, if it is within microseconds, it doesn't bother us. So even the bandwidth of the performance is reduced, as long as it is perceivable, it is imperceivable to us, it is fine. So yes, bandwidth does change the bandwidth of the system, but if that delay is within the limits, it is fine. Just hold on. So how do we do it? Should we start with the question answers? I mean, if you have any other, let me share my screen. Okay, just hold on. Any other question you have from the first 2 weeks? Just hold on. Mm,
So what is the practical significance of DTFT?
what is the? I could not hear you, Vijay.
Practical significance of the DTFT.
Yeah, practical
Okay, so
significance
what is
of.
the significance of DTFT for the reader?
Yeah, so DTFT is, you see, good question. Let's say a sine wave, okay. Uh, First of all, you should ask me that what is the significance of a Fourier transform first, and then comes a discrete time Fourier transform, right? So you have this. Let's say I want to communicate a sine signal to you, okay? So what if I do it in the time domain? What would I say? That in 0 you have a 0 voltage, in 1 you have some voltage, at 2 seconds you have some voltage. This is the way I'm going to, because sine wave is continuously changing in the time domain. But what if I go to Fourier transform? I say that Vijay, I will give you only one impulse at, let's say, 5 kilohertz. With only this information you will be able to recreate the sine wave, right? So that is the power of Fourier transform, that a signal which is continuously changing in time domain, you bring it to only one point, only one impulse in the frequency domain. Now here comes the significance of Fourier transform, that you are actually reducing the size of the data in Fourier transform. Coming back to your question, what is the use of discrete time? What is the significance of discrete time Fourier transform? Since Fourier transform works mostly in analog, how do we define it in terms of, because Fourier transform says what? Fourier transform says the signal has to be continuous, right? That is the basic necessity of Fourier transform. The signal has to be continuous. Are any digital signal, or if we want to discretize any analog signal, are they continuous? No, because we have, at 1 second we have one sample, at the second we have another sample. What about 1.1 second, 1.2 second, 1.3 second? They are all zeros. So there is a perfect discontinuity between 1 and 2 seconds. So how to deal with that? So that's why the concept came for discrete time Fourier transform. Okay, so right now with discrete time Fourier transform you can deal with digital signals. With the normal analog Fourier transform you cannot deal with digital signals, because it deals with integration, and integration is not valid for digital signal or a discrete time signal, right? So discrete time Fourier processing changes the whole game, okay, and makes it applicable for discrete time signal. Is it clear, Vijay? Hello? Are you able to hear me?
Yes, sir.
Okay. Vijay again joined.
Yes, sir.
Yeah, okay.
Clear.
Yeah. So how do we start? Do you have any other question? Let's make it a question answer session in this one. Maybe from the next session, what I'm going to do, I'm going to bring out some questions, okay, and we can start maybe solving questions. I don't have the pen and paper this time, so it will be a 1 hour session. But what is important is, can you just guys tell me any other questions that you have in mind?
So one small question I have.
Yeah.
Sir, two term is there. Discrete time model and discrete map model. Both are same or different?
See, discrete mathematics deals with all the kind of mathematics that is required for, discrete time signal. Now when you have discrete time Fourier transform is just one signal processing technique. You similarly have wavelet transform, you similarly have cosine transform, okay, they are all applicable to discretes. But when you say discrete, you are saying discrete mathematics, right?
Discrete map modeling and discrete time modeling.
Discrete math modeling, MATH.
MAP.
Discrete map modeling, I think discrete map modeling is somewhat, for example, let's say, I am not sure of this word, but what I can understand from what you are saying is When you say discrete time, it means that we are taking a continuous time series data and making it time wise, right? When you say discrete map, time can be any parameter. This x-axis can be any parameter. For a discrete time case, it is a time parameter. But similarly, you have discrete Fourier transform. So there, the axis x-axis is a frequency axis. Okay. There also you have some discrete mathematics along with discrete Fourier transform. So that is called as that maybe is called as discrete map. I'm exactly not sure. I have not heard this term actually. So can you give me some?
No, recently I have read this term in the IEEE paper, one of IEEE paper.
Okay, okay. See, I understand because see these papers, no, they use many different kinds of terms. Okay, not
Yes,
in IEEE, even
yes.
in nature.
Even even I have sent these wanted to resolve this query and have sent the email to the author, but I yet not have received any uh, communication from their side. So just as per discussion, I just wanted to know if you know.
Okay, okay, yeah. Because I think in the papers, many people use terms very contextually. Okay, rather than generally. So it may not be a very general term, and even if it exists, I mean, it may be existing very contextually. It is not a very generic term, is what I understand.
No issues. Thank you.
Yeah, Gangadharan said, why frequency domain? You go for frequency domain because in time domain the signals are very changing. Okay, so it becomes very, see, even Tesla, who was a great engineer by the way, he said that you want to understand the universe in three aspects. Okay, energy, vibration, and frequency. So I mean, this is just a quote, but the reason why he was saying this is it, many things becomes clear when you are in the frequency domain, because in the frequency domain your time parameter does not change. Okay, and in the physical domain, in the real world, you have a sensor data which is coming. It is continuously varying in time, continuously. Okay, it becomes very difficult to localize a problem. So when you want to localize a problem, you want time to be absolutely static so that you can understand what behavior is going on in the signal. So for that we need to go to the frequency domain where there is no agenda of time. Okay, there is no quotient of time. Time absolutely is freezed and you see only those things which are continuously changing, which is the frequency. So that is the reason you go to frequency domain. Is it okay, Gangadharan? For example, frequency is inverse of time, but frequency is not exactly inverse of time. So when you say frequency, frequency is the inverse of time period, not inverse of time. Okay, so for example, when we have, let's say, time 1 second, 2 second, 3 second, 4 second, time is continuously flowing. We can never say that frequency is always inverse. Okay, frequency is 1.5, 0.33, 0.25. the the way in which time is flowing, frequency is not flowing in the same way. Okay, frequency is the inverse of time period, right? So when we have, let's say, a specific time, and time period is constant. Okay, let's say you have a sine wave which is continuously changing in time, but still you say that the time period of the sine wave is, let's say, 20 millisecond. Okay, that is constant, but you see a sine wave, it is continuously changing in time, it is going up and down. Okay, so frequency does not mean it is inverse of time. Frequency is the inverse of time period. Is it?
Sir,
Yeah, Gangadharan, is
So
it okay?
if I
Yes,
want
go on.
to if I want to implement this DTFT in the FPGA,
Hmm.
can be.
Gangadharan, I'll show. Yes, I'll show. Yes. Yes, Vishwanathan and Vijay, both of you raised hands. So Vishwanathan first ask the question, then Vijay, and maybe Gangadharan will show the time period of the frequency.
sir, can I ask one question regarding Fourier transform?
Yes, sure, sure.
Sir, why energy of sampling is pi, sir? Because sampling signal, it is area is not we can't calculate directly, na, sir, because it is varying in at infinite duration. That magnitude also is not we can't directly And how it is pi, sir?
The frequent energy of the signal is pi. Who said?
Sampling signal energy.
Uh, but sampling sampling frequency is pi. Who said that?
Sir, energy, sir.
Uh, no, the energy is not pi. Who said? I mean, have you come across this text? Energy is pi. Just hold on. Huh?
Energy of sync is 1, and when pi is yeah, sync from sampling t by pi, if we do means 1/1/5 is pi.
Acha, okay, that way. Okay, I'll get my pen and paper. Just hold on. Are you able to see my screen? Hello.
Yes, sir.
Just hold on. Maybe I'll get my pen. Yeah. So you mean to say that, let's say you have something, it comes here and then it comes here. You say why it is pi, is it? In the frequency. Yeah, Vishwanathan.
Sir, energy is pi.
No,
At
energy.
x is 0, at x is equal to 0, magnitude is pi.
No, who said that at x equals to 0 the magnitude is pi? Where is it written? It is not the case, na? For example, let's say you have a sine signal. You have a sine signal. You have the sine signal. Are- Is it pi at 0? No, na?
No, sir.
Then why I mean, from where have you
Sampling signal, yes, sin t by t.
okay, let's say 1 by t, yes, 1 by t.
Sin t by t, sir.
Oh, acha, so it's a sync signal.
Yes, sir. Yes,
Sin t by t, right?
yes, sir.
Yeah. So it is a sync signal. So in sync signal, so sync signal looks something like this. Okay, so yeah, it looks like this. It looks like this. It continuously decreases and you find out this. Okay, maybe the drawing is bad because I don't have a proper pen and something. So yeah, so the sync signal is defined by sine of pi x divided by pi x. Okay, this is your sync signal. So you see at x equals to 1, if x equals to 0, what will be the value? The value is 0. Says, okay. So it starts from here 0. At x equals to half, the value is 1. Okay. So you have, let's say, you start with this, the value is 0. Then you have half. When you have half, you are actually having 2 by pi. 2 by pi here, right? And then it comes here. At x equals to 1, the value is 0 again. At x equals to 3 pi by 2, it is minus 2 pi by 3. Why? Because the moment you put x equals to 0, x equals to 1 and x equals to 2, you will see the value that you get is 0, 2 by pi, okay, then 0, then minus 2 pi by 3. So this is the way it is continuously decreasing. So is that what you want asking?
No, sir. Energy of sink is one. How it is? There, I am not understanding.
Energy of the sink is 1. You mean the sine square pi x divided by pi x integration. This is 1.
Sink by square, not square. Oh yes, sir. Pi x square denominator. Uh, they said energy will be pi for after applying Fourier transform duality like that.
Okay, maybe maybe I'll get back next time when you say I have noted down the question.
Okay, sir.
Okay, yeah. Vijay, did you have any question? Then I'll show Gangadharan. Okay, I'll open MATLAB. I'll show. Vijay, did you have any question? You raised your hand. Yeah, Vishwanathan, tell me.
Sir, in inverse Fourier transform,
Yeah.
1 by 2 pi one factor is coming, sir.
Yes,
Why
yes,
it
yes.
is coming, sir?
Yeah, it is because of the scaling. Because Fourier transform, see, Fourier transform introduces one scaling factor. Okay, Fourier transform introduces one. It is just to make sure that your time and frequency reversals are okay, because the Fourier transform introduces from time domain to frequency domain with a factor of 2 pi. So when you come back from frequency domain to time domain, you want to reduce the factor so that this transition is authentic. Okay, and that is the reason you go you say that we have to divide by 1 by 2 pi.
Okay.
It is just to keep the scaling factor constant. I mean the scaling, it is just to make the transform invariant to any scaling factors.
Okay, sir.
I'm opening MATLAB. I'll show Gangadharan how this frequency transform happens.
Sir, our duality in Fourier transform, sir. Why? There also same the 2 pi factor because of the frequency transformation from primary time to frequency, sir.
Yes,
There
yes, yes, yes. In which one? In which one? Fourier transform, right?
Fourier transform duality.
Yes, yes,
There,
same. Yes. You have this 2 pi factor. Yes, true. This MATLAB is taking some time to open. Give me 2-3 minutes.
sir, in on integrating an impulse signal to unit step signal,
Correct.
while we are adding one constant term, sir, pi del omega.
Yes. Why we are doing that, right?
Yes, sir.
Yeah, because we have a discontinuity of the step signal at 0. See, the step signal is having 0 value at t less than 0, and suddenly it has got 1 value at t greater than 0, right? The step signal. So when
Sir, again. Yes.
uh, the step signal
T equal to 0.
for t less than 0, we have value equals to 0. For t greater than 0, we have step signal as 1, right?
Yes, sir.
So what about t equals to 0? There is a discontinuity, na? So
Yes, sir.
yeah, so to manage that discontinuity, Fourier transform introduces pi del omega. So you have because of the high frequency, you have an impulse function at omega equals to 0.
Okay, sir.
Okay. Are you able to see my screen, MATLAB screen?
No, sir.
Okay, just hold on. Are you able to see my screen now? I think yes.
Yes.
Yeah. So let's say I define a sample of 1000. Okay. Now n equals to 1000. Your f0, which is the frequency of the sine wave, is 5000. Right. And you have fs, which is the sampling frequency, which is 50,000. Okay. Now we define the sine wave. How to define the sine wave? Let's say sine wave is equals to sine 2 star pi star f0 by fs star n, and let us plot the sine wave. Let's see how the sine wave looks. Are you able to see how the sine wave looks? Hello? You are not able to see? Acha, just hold on. Yes. Are you able to see now? Are you able to see the sine wave? Yeah, okay. So you see this is the sine wave, right? And it looks like a sine wave. It's absolutely fine. Let's say this look like a sine wave. Okay. Now let us see the frequency transform. So sine wave. Now you see the sine wave is continuously changing in the Fourier domain, right? In the time domain. So let's say sine wave FFT is FFT sine wave ABS. Now let's see how this looks like. So plot figure plot sine wave FFT. You see, there are no other component, but there are only two impulses in the frequency domain. So this is the frequency plot. Okay, so you have the sine plot here, this is the time plot, and the corresponding frequency plot is here. Now let us do a frequency shift. Okay, FFT shift. Yeah, so this is how the sine wave looks like. Okay, so this 500 point is the 0th point, because you have 1000 number of samples, so you have 500 and minus 500. So this is, consider this to be the 0 point. On one end you have one impulse, on the other end you have another impulse. Why? Because sine wave is a real signal, and when you go to complex domain, so you have this the corresponding negative frequencies. Okay, so you have this two sine waves, right? Clear?
Sir, the magnitude of each impulses will be half the amplitude of the sine wave, sir.
Absolutely, yes. With a factor of 2 pi.
Sir, but 1 by 2, na, sir. My doubt is when 2 sine t we are representing, we write two impulse at corresponding frequencies with half or 2 pi, sir.
No, we write in terms of 2 pi. We run in terms of 2 pi. We never write only, so the value will not be 1 and 1. No, it will be in terms of 2 pi.
We are not doing inverse Fourier transform, sir.
No, we are not doing it, but in the frequency domain we have this 2 pi factor. Because how a Fourier transform is defined?
For integration of some signal multiplied by exponential.
Correct. So in the exponential, what we have?
E power j omega t.
Correct.
Minus j omega t.
Yes, and what then that is dt, right? Then you have dt.
Yes, sir.
Okay. So in the t you see there is omega t, right? So,
okay,
so yeah, so omega comes out. Okay, and there you have this 2 pi f factor.
Omega comes in the denominator, and when it goes to left. Okay, sir.
Correct. Yes. So you have this 2 pi factor. Yes. So it may be a division, but you always represent in terms of 2 pi. Yeah. No, for triangle we do not get two impulse. We will get something else, and I would really ask you to try that. In triangle, you will not get two impulse. You will get some spread of the frequency. Okay, you will get a sinc function. You will not get impulse. It is only for sine wave you have an impulse. Only because sine wave has got only one frequency. So that is the reason you have only one impulse. You want to create a sine wave at 50 Hz? Okay, let's create. So it's very easy. So what we have to do is the same thing we will write. We will only change the f0 to, instead of 5 kilohertz, we will change it to 50 Hz. Okay, and we'll redefine the whole thing. Let's see. You see, now this is a, previously you see what kind of frequency we had, because it was 5 kilohertz, right? So the frequency was very high, but right now you see it is a very clean sine wave, right? So this is what we call as a 50 Hz sine wave, and this is the corresponding Fourier transform. Now if you zoom into it, it may appear like a single line, but if you zoom into it, there are two impulses which are very close to each other. That is a different thing, but you have two impulses. Okay. Yeah. Okay. Yeah. Any other question?
Sir, when we multiply a rectangle signal with a sinusoidal signal, then Fourier transform, how will it come, sir? We shifted for rectangles, sir. Modulation property.
No. It is not a shifted rectangle. See, the Fourier transform of the rectangle is a sinc wave, right? And the Fourier transform of the sine wave is an impulse. So if you do a convolution in the time domain, it will just be a multiplication in the frequency domain. So if I show you in terms of one note, let's say you have a continuous sine wave. Sine wave, and then you take a portion of it and you say, not this portion, let's say one signal portion of it, and then you say that this is a rectangular signal. Okay, and then the final signal that you have is looks like this. Okay, or looks like this. In the frequency domain, what will happen? What is the Fourier transform of a rectangular signal? It's a sinc, right? Sinc. And what is the Fourier transform of the sine wave? It is what? Impulse. Okay, it is an impulse. So multiplication in the time domain is basically convolution in the frequency domain. So what you do? The convolution means what? Shift and slide. So you shift this sinc wave and you slide, and finally where you will get? You will get something here. So this is what you will get. Okay, so you get a shifted sinc pulse. You get a shifted sinc pulse. This is the result when you multiply a sine wave with a rectangular wave.
Sir, but when we multiply in frequency domain,
it will be a convolution in the time domain. It will be a convolution in the time domain. Right?
1 minute, sir. Can I show that problem, sir?
Yeah.
Sir, actually the problem is f of omega is cosine cos omega multiplied by 1. We do inverse Fourier transform, and we shift cos omega as e power j omega plus e power minus j omega by 2. Then we shift, no, sir.
Tell me one more time.
Cos omega ranging from minus pi by 2 plus pi by 2.
Okay, cos omega ranging from minus pi by 2 to pi by 2. Okay. So, tell me.
What is Fourier transform?
Fourier transform, should it be a Fourier transform or a
Sorry, inverse Fourier transform. Inverse Fourier transform.
Yeah. So what it means is you have cos omega. So see, if cos omega is what it actually means is you have multiplied a rectangular function in this cos omega, right? So it is ranging from minus pi by 2 to pi by 2, right? So this is what it means. So what it means is you have one you have one sync wave. Okay, you finally have one sync wave in the time domain, and then you have another sync wave in the time domain. Okay, so what is the problem that you are facing with this problem?
Sir, modulation property, no, sir. That is multiplying exponential to cosine function to time domain and multiplying cosine function to frequency domain. There, I am not able to understand shifting and this one, sir.
Uh, just hold on. You have f omega. You have multiplied a sine cos wave, right?
Yes, sir.
So cos wave is basically e to the power j omega plus e to the power minus j omega by 2. This is what it means, right?
Yes, sir.
This is cos wave. So you see f omega e to the power j omega and plus f omega e to the power minus j omega. Okay, this is omega by 2, I guess. Omega by 2. Okay, divided by 2. So you see that f omega e to the power j omega by 2, and then you have f omega e to the power minus j omega by 2. Okay. So what you see here is, if you take the inverse Fourier transform of this and you take the inverse Fourier transform of this, so what actually it means? It
Shifted.
Yeah, what it means, what is the inverse of f omega? Because since it is a rectangular function, the inverse of f omega will be a sinc function, right? It is just a sinc function. E to the power j omega, if it comes in the Fourier transform, what it means is, in the time domain, it might have been shifted by t equals to minus 1 by 2. So you have this sync wave which is shifted by t equals to minus 1 by 2, and here you have another one which is shifted in the negative direction by minus 1 by 2. So you have addition of two sync waves. One, this is my sync wave, and sorry. So this is my first sync wave. Okay, it is shifted by half, or it is shifted by, let's no, we will take it as it is shifted by 1. So you shift it by 1, something like this. This is one you go, and you have another one which is shifted in the negative direction like this,
Yes, sir.
and you add them up. So this is what you get in the time domain.
Sir, but when we apply like for constant using duality property 2 pi del omega for exponential shifted cos also is shifted pi del omega na sir, pi by 2 del omega plus omega naught. When we do that, this is different na sir.
No, I'm not understanding. Can you do one thing? You have my mail ID.
No sir.
Yeah, do one thing. You take my mail ID and you mail me the problem. Wait. Yeah, you mail me the problem. I'll solve it by tonight and give you.
Okay.
And you also write down what you feel about that pi by 2 del omega and all. That is also fine. Okay. Maybe so next week again, maybe we can see whatever problems you have, you keep mailing me in this Gmail. Okay, so I can keep answering your questions even in between the week, and maybe we can meet next week.
Okay, sir. Thank you, sir.
Gangadharan, was it okay? Your MATLAB wala portion? Yes, YouTube link also I'll give. Okay. Yeah, Vijay, was it okay?
Yes, sir.
Okay, fine. Yeah. You can always mail me all these problems. Vishwanathan, you mail me the problem. Okay, right now.
Okay, sir.
Check. ठीक है, you can leave. Bye bye. See you.
Bye, sir.
Yeah. Hello, Sri Harshita. Do you have any questions?